Hey, my name is Stephen Akers, and today I'll be reviewing what I have done for Lab 5 called Magnetic Braking with Faraday. So, the whole purpose of this lab is to basically observe how a barred magnet flows through a conductor and see how the induced currents affect the barred magnet's motion through the conductor. And yeah, the way that we're able to figure what's going on with that is through Faraday's law. As you can see, we have established a rule that the negative change of flux over time will equal an EMF, and that's what we're seeing with the induced currents happening. The only materials that we're going to be using here will be a barred magnet and some aluminum foil. So for the experiment portion of this lab, the basic goal of this is to just drop a barred magnet through a floor roll and then just record the times that it takes for that magnet to fall out of the roll. Now, like the expectations here is that we should see like some type of interaction happening with the magnet and whatever conductor that we're using, right? And so like when comparing it to free fall, there should be an obvious difference in like the time that it takes for the magnet to actually fall like through the roll. But as you can see, with my recorded times, it doesn't seem to be that way for me. Like there doesn't seem to be any interaction happening with the magnet and the floor roll. As you can see, like 0.3 seconds and 0.4 seconds, those seem like free fall times. And I did try to, so yeah, I actually did a test where I would see so I dropped the barred magnet through the floor roll first, right, as you can see in the GIF, and then I also did it without the floor roll just to see how it is with freefall, and they were basically the same. Without even having to record the times of them, they just seemed the same. So I concluded that I probably have some pretty bad magnets, and yeah, they're just messing up my results altogether. Because I also had some problems with Lab 3 as well with magnets, where I was getting like really wild results, like just a crazy mu value, and then like yeah, just totally messing it up for the coding portion as well. So like at first I thought there was like maybe a problem with like my phone like not picking up the magnetic field correctly or something. So I kind of put it off, like maybe the magnets are still working, but yeah, the second lab kind of just put the hammer in the nail for that. That my magnets just suck. So, but yeah, I did get an average time of around 0.38 seconds. But like I said, that just seems like free fall, so it's kind of useless in this case. So, but yeah, hopefully, yeah, my dog in this GIF can cheer you guys up instead of seeing some good results. Now for the coding section. Here I had to make up a mu value because, like I mentioned before, I got some wrong results for lab 3, and I didn't want to deal with that mess in this lab again. So yeah, I just tried to make a guess for that. And then yeah, the real meat and potatoes of the coding is the function for the magnetic field from the barred magnet, as well as the function for the change of flux that we're going to be using for the conductor. Um, and yeah, I'm still not able to get a proper or reasonable results that emulates what would happen in real life. As I get a result of around 4 seconds, and I'm not too sure if this is due to if this is due to the mu value that I use, or just maybe something else that I don't see in my code. But yeah, it's kind of hard to determine that without like a real life model to use as a reference. So yeah, I'm not really able to, I guess, figure out what's the issue for me. All right, so now for the post-lab questions. So what would happen if the resistivity of the conductor was reduced as close as possible to zero, and how would that change the dynamics of the falling magnets? So here I use Ohm's law. I mean, really, I just use the middle formula of the picture that you see, of I equals V divided by R. And so in this situation, we know that R is going to be close to or pretty much equal to zero. And we know there is going to be like a non-zero V voltage value, simply because there's going to be like the interaction of the barred magnet flowing through the conductor. That's going to generate a non-zero EMF and a value for voltage. So basically, we have a number divided by pretty much zero, and just basic math, we know that's going to equal to infinity. So we know that the current will equal to infinity. And this would result, like, since the current's infinity, so would the magnetic force would also be pretty damn big. Um, so yeah, when the magnetic force is just basically infinity that's acting upon the bar magnet's no longer to be able to fall through anymore through the conductor. Yeah, it's just not going to happen. So, yeah, for question 2, what if holes or slots were cut into the tube, and how would this affect the ring's currents in your model? So here I kind of had to make an educated guess on this. So my way of thinking was that, so now there's going to be less rings, and therefore there's going to be less magnetic forces acting upon the bar magnet as it like flows through the conductor. So yeah, my way of thinking was like, okay, now maybe the bar magnet is able to, I guess, fall faster through the conductor now, since it's not as many forces acting upon it anymore. But this will also result in an increase in the change of flux over time. So, yeah, because since the bar magnet is now increasing the velocity, so too will the change of flux over time with if we just look at a single ring on the conductor, we're going to see an increase in that change of flux over time. And so, due to that increase, now we're going to have larger currents with each of those rings inside the conductor. So yeah, basically there's going to be an increase.